Hi, and welcome to the world of instrumentation and control. In our last video, we talked about the RTD, or Resistance Temperature Detector. Today we are going to talk about the instruments that are used with RTDs and the wiring configurations that are used to connect those instruments to the RTD. In our last video, we described RTDs as a type of temperature measuring sensor that operates on the principle that metal wires change their electrical resistance in response to changes in their temperature. Therefore, in order to know the temperature of the RTD, we need to measure its resistance and then convert that resistance to its equivalent temperature. There are several types of instruments that are used with RTDs. We'll go over each of them in turn, and after that, we'll talk about the different wiring configurations. The first instrument we're going to talk about is the resistance meter, also called the ohmmeter. These devices only measure resistance and do not convert the resistance to the equivalent temperature. To find the equivalent temperature, you will need to use an RTD temperature versus resistance table. These are documents that will allow you to look up the temperature and find the resistance of the RTD at that temperature. You can also use it in reverse. You look up the resistance and find the temperature that represents that resistance. There are several types of RTDs in terms of material, nominal temperature, and temperature coefficient. Each type of RTD has its own temperature versus resistance table. So make sure that you know what type of RTD you have and that the table you are using matches that type of RTD. The second instrument we're going to talk about is the temperature transmitter. These types of instruments measure the resistance of the RTD and then converts that resistance to its equivalent temperature, and then converts that temperature to an electronic signal that can be transmitted to another instrument or piece of equipment up to a kilometer away, depending on the type of transmitter. The third type of instrument is the temperature indicator. The temperature indicator can measure the RTD's resistance and display the equivalent temperature. Some models of temperature indicators also have the provision to act like a transmitter in that it can transmit the electronic signal equivalent of the temperature to another instrument some distance away. A similar instrument is the temperature controller. Most models of this instrument can also display the temperature, but in addition can also control the temperature of whatever equipment it is connected to. It may also include the capability to transmit the electronic signal equivalent of the temperature to another instrument. Transmitters, indicators, and controllers come in many forms and capabilities. When you use these instruments with RTDs, it's important to know the characteristics and capabilities of these instruments to make sure that the instrument is capable of accepting RTD sensors and that it can accept the particular type of RTD you are using. This is a special type of instrument. It's called a calibrator. And one of the things it can do is measure and display the resistance of the RTD as well as its temperature. It can also simulate or mimic the operation of the RTD so that you can use the calibrator to test or adjust the instruments for correct operation. This is just some of the things calibrators can do, but we'll talk about them in a future video. The last type of instrument that you can use with RTDs is the ordinary digital multimeter. Similar to the resistance meter, it can only measure the resistance of the RTD, but not display the equivalent temperature. Unlike the resistance meter, however, the digital multimeter is better suited to testing the RTD rather than being used to measure its resistance. Okay, so those are the different types of instruments that can be used with RTDs. Now we are going to talk about the different wiring configurations that are used with these devices. But before I do that, I think I need to explain how resistance is measured. There is no instrument that can measure resistance directly. Instruments measure resistance by applying an electric current through the component or device and then measuring the voltage drop across it. Then, using Ohm's law, the instrument calculates the resistance by dividing the voltage by the current. Other circuits inside the instrument will then convert this resistance to the equivalent temperature. And that's how resistance is measured. I think it's important for you to know this before we go into the details of how RTD instruments work. And one last thing before we proceed to RTD measurement. The circuits that I will be showing you is only one possible type that is used by RTD instrument manufacturers. Other manufacturers may have different methods for measuring RTD resistance, but these are beyond the scope of this video. Now, there are three wiring configurations that can be used with RTDs: 2-wire, 3-wire, and 4-wire. Each has its own pros and cons, although some instrumentation professionals might say they prefer one over the other. Let's go over each of them in turn. The 2-wire configuration is the cheapest, simplest, and least preferred wiring configuration. Cheapest because it only requires 2 wires. Simplest because, at the very least, you only need to make 2 connections. And it is also the least preferred because it introduces the largest error to the measurement. Why is that? Let's look at a simple 2-wire RTD measuring circuit. Let's say that the RTD is a PT100, that is at 0 degrees Celsius. That means its resistance is 100 ohms. Notice that the voltage measuring circuit is connected across the RTD and the 2 wires, RW1 and RW2. So, when the instrument measures the resistance of the RTD, it is actually measuring the resistance of the RTD plus the resistance of the 2 wires. So if each of the wires has a resistance of 0.1 ohms, the instrument will see 100.2 ohms instead of 100 ohms. Converting that resistance to temperature, our instrument will display 0.51 degrees Celsius instead of 0 degrees Celsius. So, a 2-wire configuration adds the resistance of the 2 wires to the RTD's resistance. Since a wire's resistance increases with length and with smaller diameters, longer and thinner wires mean bigger errors. So if you're going to use the 2-wire configuration, shorter or thicker wires is the way to go. Next, let's look at the 3-wire configuration. Since it uses an extra wire, the 3-wire configuration is more expensive than the 2-wire configuration. It is also a bit more complex because you need to make at least 3 connections instead of just 2. It is, however, the most used wiring configuration, mainly because it is midway between the cheapest and the most expensive, and midway between the simplest and the most complex wiring configuration. What about the accuracy? Notice that in the 3-wire configuration, the voltage measuring circuit is connected across the RTD and RW2, whereas in the 2-wire configuration, the measuring circuit is connected across the RTD, RW1, and RW2. So, in the 3-wire configuration, RW1 has been removed from the measurement, and the voltage measuring circuit is only measuring the voltage across the RTD and RW2. Therefore, the error has been cut by half. If the RTD is at 0 degrees Celsius, the circuit will measure the resistance as 100.1 ohms, and the equivalent temperature becomes 0.26 degrees Celsius instead of the true temperature of 0 degrees Celsius. But wait a minute. What about RW3? Doesn't it contribute to the error? Yes, it does, but its contribution to the error is extremely small. So small, it's safe to ignore it. How is that? The voltage measuring circuit has a high input resistance, as high as 10 megohms or more. That means that the current passing through RW3 is very small, in the order of picoamps. That means that the voltage drop across RW3 is equally very small, in this case, about 1 nanovolt. So the voltage at the input of the voltage measuring circuit is almost the same as the voltage across the RTD and RW2. There is a circuit for the 3-wire configuration that can effectively eliminate the error caused by the connecting wires. I'm not sure if there is an instrument manufacturer that uses this circuit, but if no one's using this circuit right now, then I will be giving them an idea. The circuit uses a selector switch. In position A, the circuit will measure the resistance of RW1 and RW3, which in this case comes out as 0.2 ohms. Let's call this as resistance A, or RA. Other parts of the circuit, not shown here, will store this number in memory. Then the selector is set to position B, which sets the circuit to measure the resistance of RW1, RW2, and the RTD, all of which comes out as 100.2 ohms. We'll call this as resistance B, or RB. Finally, the circuit retrieves the value of RA from memory, which in this case is 0.2 ohms, and subtracts it from RB, which gives us the resistance of only the RTD, and that is 100 ohms. This method, therefore, eliminates the error contribution of all the wires. There is, however, one requirement for this method to work, and that requirement is true for other 3-wire resistance measuring circuits. All 3 wires must have the same resistance. That means that all 3 wires must have the same length, the same size, and material. Any difference in resistance among the wires will result in errors in the measurement. Another disadvantage of this method is that the measurement of the RTD's resistance will be done at intervals instead of being continuous. But if the switching between position A and position B is frequent enough, this should not be a problem. Okay, now let's look at the 4-wire configuration. The 4-wire configuration is the most expensive, most complex, and produces the most accurate results among all the wiring configurations. Most expensive because it uses the most number of wires. Most complex because it requires at least 4 connections. And most accurate because, well, you'll see. This is what the 4-wire configuration looks like. Notice that the measuring circuit is directly connected to the RTD via RW3 and RW4. RW1 and RW2, therefore, are not included in the measurement. As before, the measuring circuit has a high input resistance, so the current flowing through RW3 and RW4 is very small, and consequently, the voltage across the RTD and the voltage at the input to the measuring circuit is almost the same. So, if the voltage across the RTD is 0.1 volts and the current going through it is 1 milliamp, the measured resistance is 100 ohms, exactly the same as the resistance of the RTD. Note that with the 4-wire configuration, the requirement for the same length, size, and material of the connecting wires is not required, although following the requirement is still good practice. So those are the 3 wiring configurations that can be used with RTDs and the principles by which they operate. What have we learned so far? Number 1, with the 2-wire configuration, the measured resistance will be the resistance of the RTD plus the resistance of the 2 wires. Number 2, with the 3-wire configuration, the measured resistance will be the resistance of the RTD plus the resistance of only 1 wire. Number 3, in the 3-wire configuration, the resistance of the 3rd wire adds very little to the error, such that it can practically be ignored. And number 4, with the 4-wire configuration, the measured resistance is almost the same as the resistance of the RTD. So, from all of this, it seems as if the 4-wire configuration is the only way to go. Not so fast. Back when I was starting in the field of instrumentation, 1985, I came upon a rule of thumb regarding what wiring configuration to use for RTDs. It was called the multiples of 2 rule. It goes like this. If your wire length is less than 2 feet, use the 2-wire configuration. If your wire length is less than 20 feet, use the 3-wire configuration. If your wire length is less than 200 feet, use the 4-wire configuration. Now, I've learned a lot since 1985. It's been 38 years since then. And I have to say that this rule is a little too simplistic. Most RTDs are assemblies where the RTD sensor is inserted into probes that are anywhere between 50 to 1,500 millimeters in length. A lot of times, these probes have transmitters included in the assembly. If your probe is less than 2 feet long and has a transmitter included in the assembly, it's okay to use the 2-wire configuration. If your probe is more than 20 feet long and has a transmitter included in the assembly, it's okay to use the 3-wire configuration. Now, probes that are 20 feet long are very rare, but probes that are about 5 feet or 1.5 meters long are available, and you can use the 3-wire configuration with them. However, if your wire goes outside the probe and is connected to a transmitter some distance away, I would recommend that you use the 4-wire configuration even if the total wire length is less than 20 feet. Why? When your connecting wires are exposed to the environment outside a probe, such as if your wires are exposed to the sun, for example, its resistance will change with changes to its temperature. So instead of a constant error, your RTD measurement system now has an error that changes, and that will complicate the accuracy of your measurements. The 4-wire configuration, however, is able to make accurate measurements even if the connecting wires change resistance. But wait, if the 4-wire configuration is so good, why is there a 200-foot limit? When your wires become very long, the benefit of the high input resistance of the measuring circuit will eventually be negated, and you will start seeing increasing errors in your measurements. So what can you do to minimize the errors in your measurements? One solution is to include temperature transmitters into your probe assemblies. Your connecting wires will be shorter, and consequently their resistances will be very small, resulting in smaller errors. Another solution is to use RTDs with higher nominal resistances. RTDs such as PT200, PT500, and PT1000 have resistances that are much higher than the resistance of the wire you typically use. And that means that the effect of the connecting wires will be much smaller compared to a measuring setup using a PT100. The best solution is to calibrate and adjust the measuring instrument while it is connected to the RTD. By doing this, the instrument will take into account the wire resistance as well as the inherent error that the RTD has and produce temperature readings that are accurate. Remember, always calibrate your temperature instruments together with the RTDs that are connected to them. And that's it for our presentation about the instruments that are used with RTDs and the wiring configurations they use. I hope you learned something today, but even if you didn't, we have lots more videos to come. I worked in this field for 37 years, and I can't say I stopped learning at any point during those years. I'll see you next time in the world of instrumentation and control.